Hi all. We have one more variation of the aldol reaction before we get to other reactions that use the enolate. And this reaction is called directed aldol. It's a way to run across aldol by making the enolate with LDA, lithium diisopropylamine. Let me show you how this is done. Let me add a subtitle to this. It's a way to run across aldol by making the enolate with LDA. Or we could say by converting all of the carbonyl to enolate. How does that help us? Well, if we could convert all of this to the enolate, then we could throw in any other carbonyl, in this case ethanol, and then we'll do a cross reaction. The enolate will attack this carbonyl with no danger of this becoming the enolate, or with no danger of this attacking another one of itself. Let me walk through this set of reactions. We have LDA. If you recall from, I think either the first or the second video, we discussed that LDA is a very strong base. This should be review. LDA, lithium diisopropylamine, so it's a base. And what's good about this is that when it does its thing and rips off an alpha proton, you get this conjugate acid, which has a pKa, we should all know this, around 36. So it's a very weak acid, meaning that this is a very strong base. I think what's best here is to show you the mechanism and then remind you what would happen if we use the regular base that we usually use, like hydroxide or ethoxide. So the first issue is this. We have an unsymmetrical ketone. Do you remember what happens when we use LDA with an unsymmetrical ketone? Let me give you a hint. We're either forming the kinetic enolate or the thermodynamic enolate. We are at very low temperatures. Let me just go up here. We're using LDA, strong base, bulky base, crowded base, at very low temperatures. My thinking is that you will make the kinetic enolate. Where am I going to write that? Make the kinetic, not the thermodynamic, enolate. It's good that it's bulky because that will help us push towards the less crowded alpha carbon to make the enolate on this carbon. But also we have very low temperatures. So once we make the enolate, it's not going to reverse and try to make the more stable enolate, which would be up here, removing this alpha proton, sorry. Okay. You'll review if you're not quite sure what I was talking about when I discussed the kinetic enolate versus a thermodynamic. But let me find actually what video that was, just to remind you all. It was 08B50. Do you remember this discussion here? LDA, very low temperatures, kinetic, versus if we use the normal hydroxide base, we get the major thermodynamic, the more stable enolate. Okay, so that's a good reminder. So we're going to form the enolate at the 4 o'clock position. And you know that I like to give the oxygen anion form of the enolate. Not only that, I'm not going to draw equilibrium arrows. We're going to get 100% of this enolate. Double bond O minus, and there's your methyl group. And we're done. Well, I like to draw every product at each specific step. and we have this. As I said before, this is a pKa of around 36. Do you remember the pKa of a ketone? The pKa of a ketone is 20. The pKa of an aldehyde is 17. Anyway, it favors the right overwhelmingly. You're going to assume that you have close to 100% of this, meaning that there is no ketone to attack. This enolate is not going to attack another one of itself because there is none. There is no ketone left over. So that's great, because in the second reaction, we could add any carbonyl compound we want, right? And hopefully get one product, one predominant product. Ethanol is a 2-carbon aldehyde, like that. And the common name for this is actually acid aldehyde, but I use the IPAC here, ethanol. Do you remember how to do the attack? You remake the carbonyl bond. Where am I going to go? I'm going to go under here to hit the dot, and I'm going to make the O minus. Okay, let's see if I can draw the product correctly. We have this carbonyl. Okay, so we added something on this alpha carbon. We added the dot, and we have this O minus, and on that dot we have a methyl. Now think about the conditions that we have listed up here. We have the enolate, we added ethanol, okay, and then we isolate this. So you may be wondering, well, are we going to do a condensation, or should we do a condensation? Well, right now we can't. We're not under basic conditions. And even if I run the last reaction, I purposefully use water and not sodium hydroxide. So all I'm going to do is I'm going to protonate, and that's where we're going to end after this third reaction. So this is interesting. We normally don't stop at the hydroxyl group, right? Normally we do a dehydration. But again, every time we've done a dehydration, it was under basic conditions. We had an OH to remove what? To remove this alpha hydrogen right here. Okay? So let me just draw that, and we stop here. If these are the three reactions, we got to remember that since we're not under acid or base, we do not do any dehydration. Now we haven't seen a lot of, I don't think we've seen acid catalyzed dehydration in this unit, but you know from from Organic Chemistry 1, you could do acid catalyzed dehydration of an alcohol. Remember that? So I'm not saying anything that you shouldn't know already. Here, we're going to stop. Stop at the aldol product. Because if there is no base, okay. Now I understand we have base up here, but when you have a sequence of reactions, you isolate the intermediate product and you purify it. You get rid of all the solvent, all the catalyst. So after this reaction, before we add the ethanol, we get rid of all of the LDA, and we just have this anion carried forward. So if there's no base at this point, right, or acid, what, like NaOH or H2SO4, don't do condensation, don't eliminate. So we call that aldol condensation, but we know that that condensation is basically a dehydration, an elimination of water. All of those words mean the same thing. Condensation, dehydration, which is the same as eliminate, like elimination of water. Okay. Now, sure, if you want to make the Aldol condensation, if you want to make the conjugated system, all you need to do is go ahead and take your aldol product and add base. Okay, either add NaOH and water, or you know that you could do acid catalyzed dehydration. So, or H2SO4. I teach it with heat. Okay. And you will form the more stable double bond, which is going to be what we call conjugated to that carbonyl group. And it would look like that. I'll draw the methyl group going down. Okay. The last thing I want to mention, looking for a piece of paper, is, again, this is by using LDA. Now, if we had used NaOH, what could have happened? Well, we wouldn't be able to do a directed aldol because we would have a little bit of the enolate and some of the rest of it being the carbonyl. I just want to contrast again why the choosing of LDA at low temperatures is so very important, because we get 100% of the enolate. But if we use NaOH, this is just review. I know all of you know this already. If I give this reaction on an exam, NaOH, oh, this one's actually kind of interesting. We're going to make the Thermodynamic Enolate, which looks like this. Yeah, this is interesting. Right? Thermodynamic, the more stable double bond. But again, this is an intermediate because your conjugate acid is actually more acidic than this molecule here. Oh, we're going to a deep dive review session right now. So this is pKa equals 15.5. Again, this is a pKa equal to 20. So we do have a lot of the unreacted carbonyl. So you normally do this without drawing all the intermediates, right? But I just want to draw the intermediates and speculate what might happen. So you're going to get this attack. I'm not going to draw mechanism arrows, but you know the attack. And this is what's interesting to me. So there's your methyl, and you attack the dot. Right there. So on that dot, what do you have? You have... How do I want to draw this? Oh boy. You have that dot, and that dot became an OH. OH. Because you have water in the solution. Now the thing is, do you notice that I cannot do the dehydration here? Right? That would be the conjugation. That would be where the double bond would take place if I wanted to be conjugated. But I have no alpha hydrogen here. So again, I wasn't expecting this. This goes into a bit deeper than what I had expected to do. Instead, we're going to do the dehydration to make the most stable double bond, which would be here. It would be tetra-substituted. So, don't worry. I'll refocus us in just a bit. But we have this. Let me draw it this way, actually. A double bond right there. It is impossible, is what I'm saying, to put the double bond where we normally would put it. Right? We would normally put it between the alpha and this dot right here. Okay? But again, the purpose of this particular video was not to do an aldol condensation. It was to do a directed aldol in which we form 100% of the enolate using LDA. And that way we could add any other carbonyl. So it is crossed. right? We have this carbonyl and this carbonyl. Okay, so I'll leave it at that. This is, again, the last variation of the aldol reaction. We are going to go look at other types of enolate reactions that, if you know the aldol very well, though, it's going to be very, very helpful for the next set of reactions.